So today we're presenting the paper on contrastive learning with adversarial examples, presented by Kwok Lei, Saeed Rahman, William Sarin, and Eric Watson. A few details about the paper. The paper was written by Chi Hui Ho and Nuno Vasconcelos. The paper was published in the 34th Conference on Neural Information Processing Systems in 2020 and has 4 citations. As an overview of our presentation, we'll begin with an introduction of the paper. We'll delve into the related works. We'll discuss leveraging adversarial examples for improved contrastive learning. We'll just discuss the experiments, and we'll finish with the conclusion and the for and against points to the paper. So contrastive learning aims to group original and augmented images closer and original negative samples far from each other. So in many contrastive learning algorithms, we take an image from the data set. This is often referred to as the anchor. So we usually take an image from the data set, and this is often referred to as the anchor. And then we apply some augmentation poly, some transformation to create an image very similar to the original image. And together these would form a positive pair. In addition to the anchor or original image, we take another image very different from the image. This image might be randomly drawn from the data set as well. And this would form the negative image. And together these would form a negative pair. And then the contrasting learning algorithm attempts to group the images in a positive pair closer together, and it attempts to separate the images in a negative pair further apart. And usually this is achieved by sending each of these pairs into a neural network, an encoder that converts these pairs into feature maps or feature vectors. And then some similarity metric, for example, cosine similarity, would be used to group the images in a positive pair closer together and the images in a negative pair further apart. The problem is that prior works do not address this, the selection of challenging negative pairs. So what I mean by that is much of the previous work is focused on designing an augmentation polity, some transformation to the original image that creates a good corresponding pair that would lead to improved performance in contrastive learning. And so while improved contrastive learning is important, it's also important to have design a good negative pair. So if the negative image is too close to the original image, this may not induce a large enough contrastive loss in the contrastive learning, and this can cause the contrastive learning algorithm to not converge. And so it's important to develop a good negative pair as well. And so the author in this paper proposed a solution to this, which they call contrastive learning with adversarial examples, abbreviated CLAE. And this algorithm attempts to leverage adversarial examples to generate not just diverse positive pairs, but more importantly, challenging negative pairs. And the intuition behind our algorithm is if adversarial images are challenging for for neural networks enough to cause them to misclassify, then perhaps they can be seen as challenge examples for the contrastive learning algorithm as well. But the authors are careful to note that the goal in this paper is not to enhance robustness to adversarial attacks, but to produce a better representation for self-supervised learning. So the focus of this work will be on contrastive learning for the downstream task of image classification. And so while contrastive learning can be applied to a multitude of different applications, for example, it could be applying in the computer vision domain, it could be applied to image segmentation, object detection, activity recognition, or in the natural language processing domains, such as machine translation, sentence classification, language models. This paper will be focused primarily on image classification, using contrastive learning for the downstream task of image classification. So recently, contrastive learning has been used in the self-supervised learning setting. So in machining, we could think of machine learning being divided up into two categories: supervised learning, where we have a data set where each of the data points have labels to them, or unsupervised learning, we have a data set where none of the data points have labels. And self-supervised learning tends to will fall under the self-supervised learning. So we're dealing with data sets that have no labels. So contrasting learning, so annotating data sets with clean labels tend to be expensive, slow, and error prone. And also in some cases very difficult to come by. And for example, when we're dealing with medical data. So self-supervised learning attempts to eliminate human annotated labeling, has the computer automatically generate the labels. So the authors proposed a solution, apply their proposed CLAE solution technique to two other self-supervised learning methods. The first being unsupervised embedding learning, abbreviated UEL, which uses an objective function to discourage different variants of the image from being recognized as the same instant. And the other self-supervised learning method is called Simple Framework for Contrastive Learning of Visual Representations, abbreviated SimCLR or SimCLR. And SimCLR uses a projection head to avoid information lost during pretext training. And after the training, we discard the head and use just the high-level features from the SimCLR algorithms for optimizing downstream tasks. So here, let's take a look at the unsupervised embedding learning model, which the authors apply their method to. So here in UEL, unsupervised embedding learning, we first draw a random set. We draw a set of random samples from the training data. In this case, we draw 3 examples, and then we apply some data augmentation policy. So in the case of the UEL algorithm, they apply random cropping with resizing. They apply some color distortion, random color distortion. They also apply random grayscale, and as well as they also apply random horizontal flipping. And then they send both of the set of images, the original images and the corresponding augmented images, into two neural networks that are identical in architecture and share the same weights and parameters to produce low-level feature vectors. And so, for example, image x1 would be converted into feature vector f sub 1, and f sub 1 would be very similar to feature vector f sub 1 hat. And so the algorithm trained on contrastive loss would attempt to group these images. These would form a positive pair. So they would, the algorithm would attempt to group these images closer together. And it would attempt to keep these images, the feature vector of f1 compared to f2 and f3, it would tend to keep these images further apart from f1, and these would form negative pairs. So here in the feature vector space, these images would be grouped closer together because they're similar, but they would be grouped further apart from these images, which are different. The second method, self-supervised learning, that the apply their solution to is called SimCLR, SimCLR. And here in this algorithm, an image is drawn from the data set, and an augmentation policy is applied to them. In this case, for the SimClear framework, they apply a set of one of three random transformations. They apply random cropping with resizing. They apply grace. They apply some color distortion, and they also apply some Gaussian blur. And each of these transformed images are sent to an encoder to produce high-level vectors. And each of these high-level vectors are further sent to a projection head. This projection head consists of two dense layers and a ReLU activation function to produce two vectors that are conducive to optimizing contrastive loss. And then the contrastive loss function attempts to maximize the similarity between these two vectors. After training is complete, the projection head is discarded, and these um, final high-level feature vectors are then sent down to a downstream task. In this case, for this paper, the downstream task is image classification. From here, Saeed will take over discussing more information about contrastive learning.
All right, so I'm going to describe the training method that they came up with. And so their goal here is to find a pair of images that maximize a loss function. And their idea is that by maximizing the loss function, you create the best representation for the model to learn during the self-supervised learning. And the best augmentation pair is determined by maximizing the contrastive loss function here. So I know there's a lot going on. So we have T here, which is a set of transformations, and P and Q are a randomly sampled transformations, and they're different, and they're applied to the image labeled XI. And so we have XP and XQ. And so here we have in the numerator, we take our model and we input the augmented image XP, and we get the weights of the model for that image. And we do the same thing for XQ. And so we take the weights of these two augmented images and calculate the inner product of the two. And so this inner product represents the similarity or distance between the two weights. And then they're scaled by a temperature parameter.
So these are not really weights, these are features. Weights are the weights of the network typically. These are just features of this particular, yeah.
In the paper, they refer to them as weights. So I was just keeping consistent with the nomenclature they use, but yeah, they are features. And then, so in the denominator now, we keep XQ, the features for that, and we calculate for each image in the batch size B, we input that image into the network and get the features for that, and then calculate the similarity between that image and XQ. And so basically in the denominator, we're finding the sum of all the features in the batch size and their similarities between each other. And we divide by the two to get the loss for a particular pair of images. And so the pair of images with the largest loss is chosen after we sample through each pair of transformations in the set. The issue here is it's ambiguous to figure out which transformations to use that would generate the highest loss. And so the authors suggest that we fix one transformation XQ and generate an adversarial example to maximize the loss. And so in this equation here, we have the set of transformations. And so we use one transformation on XQ, and we calculate a set of adversarial examples for that transformed image. And then the adversarial pair image is determined based on which adversarial image will generate the highest loss with the transformed image. And the idea here again is that the XR, which is the adversarial image, and XQ, which is the transformed image, will help create a more robust representation for the model to learn on. And now the issue here is that we need to figure out how to generate these adversarial examples. And so the authors propose we can use the contrastive loss function as cross entropy. So here we have the standard contrastive loss function. And so here we have f theta and we have the input image. And if we think of the features as a set of weights, we can make this substitution in equation 2. And this gives us this form right here, which we can see is in the same format as cross entropy loss. And so we can use the cross entropy loss to generate the adversarial examples. So again, if the equation used to generate the adversarial image with the contrastive loss function, we can replace with cross entropy here. And here again, we have the features for the image, for the perturbated image. And so by using the cross entropy loss, you can use pretty much any adversarial attack. And the authors chose to use fast gradient sign method here to generate the adversarial image XR. And so now to fully train the model, they use 2 separate batch normalization layers. They have one batch normalization layer for clean images and one batch normalization for adversarial images. And they're training the model using both clean and adversarial images. And so the loss function they use combines the 2 type of images. As we can see here in this is the loss function here. And so the first part is the loss function for calculating between 2 transformations. And then the second part here is for the loss function between the adversarial image and 1 transformation. And so to visualize their process here, they take 1 transformation labeled in red here and a different transformation. And both transformations are sent to a classifier, a model, and the weights, the features here are returned for both images, and the inner product is calculated. And then from the loss function here, they back propagate to generate the adversarial examples and get the gradient, or to get the gradient and calculate the adversarial examples. And then for the final loss, we have the same 2 augmented images, and their inner product is calculated, and the loss function for those 2 images are calculated. And then the adversarial examples and only 1 set of the transformed images are used, and their features are retained, and the inner product is calculated. And then the contrastive loss between those 2 pairs are calculated, and the final loss is the summation of both loss types. And now Eric will explain the experiment section.
So for experiments, we use the following data sets. They use the CFAR10, CFAR100, and Tiny ImageNet datasets. They use the following contrastive loss baseline models. They use the plain contrastive loss that was just derived earlier from Saeed. They use the UEL baseline loss and then the Sinclair baseline. For the model they did for experiments, they used a Resident 18 model that was as an encoder that was trained using their contrastive learning with adversarial examples framework with the alpha hyperparameter set equal to 1. They also use a batch normalization momentum of 0.01, and they also use different batch sizes and epochs for the data sets. So for the CFAR10 and CFAR100, they use the batch size of 256 for 1,000 epochs, but for Tiny ImageNet, they use a batch size of 128 for 200 epochs. And they use the following evaluation protocols for downstream tasks. They use the k-nearest neighbor classifier with a k value of 200, And then they use the logistic regression layer that they added at the end for logistic regression classification. So first, for experiments, they determined the influence of their adversarial examples for both pre-text and downstream tasks. So in order to compare their adversarial examples, they compared the contrastive loss against random noise generated, and it's shown that their FGSM perturbations actually achieve like a higher loss. So that means it generates more challenging examples. And for the downstream, they then focus on the cross entropy loss, and they do the same methods done with the contrastive loss, and they found that their FGSM adversarial perturbations have a higher loss than the random noise perturbations. And they also show some examples from Tiny ImageNet where you have two clean images along with what the adversarial images look like, and the difference, which is also amplified to scale for viewing. So they also found out that adversarial attacks are weaker for self-supervised learning, and they only downgrade the downstream classification by over only 20%. And they compared this. They did like analysis where they took a random block from a ResNet model and sampled 40 of the channels, and they found out compared with the clean and adversarial examples, there is not like a significant difference between the mean and variance. Which they also mentioned previously. There's another paper where they did self-supervised learning. I mean, supervised learning, and there's actually a significant difference for that other paper. But for adversarial examples for self-supervised learning, there's not much of a difference. So they then do a baseline comparison where they use their contrastive learning with adversarial examples framework for self-supervised learning, and they do it for two downstream classifiers. So for the 10 nearest neighbor classifier, the epsilon is 0 means that the images are clean. Well, they also use the perturbation size of 0.03 and 0.07, and it's found that the perturbation size of 0.03 for UAL performs the best for the 10 nearest neighbor. And even though 0.07 isn't the best here, with exception for a case for CFAR10 for Sinclair, it actually still outperforms the baseline method. And for the logistic regression classification, the Sinclair model performed the best with the epsilon value of 0.03, and the epsilon value of 0.07 wasn't the best, but still outperformed the baseline classification accuracy. So next, in order to further verify the results, they did an ablation study where they use the Sinclair framework with their adversarial examples with the logistic regression classifier, and they use the CFAR 100 dataset. So they studied the following parameters, which was the batch size, the embedded dimension size, the hyperparameter value, the attach strength, along with the epoch count, and transferring their method to other datasets, and the attack methods. So for the batch size, they found out that larger batch sizes with the adversarial examples improve performance and actually outperforms the baseline methods as shown here. Using the perturbation max perturbation of 0.03 actually performs the best in all cases, outperforming 0.07. And it's shown that increasing the batch size, that even with the lower batch size of 64, it outperforms the larger batch size of 256 for baseline, showing that the adversarial examples improved the accuracy. So they also did the embedded size, and they found out that there's no significant difference. So when they increase the embedded size, it leads to no accuracy improvement for. So then they go through the architecture nets. They compare their Resonant 18, 50, and 101 architectures, and it's shown that the adversarial training, especially for the perturbation 0.03, drastically improves the performance, which is due to the fact that The reason the 15111 performs better is that they have a larger learning capacity, so they're able to learn more from the challenging examples. And even using the adversarial examples for Resident 18, it actually outperforms even the larger models that run on the baseline. So I'll let Watch continue this part.
So continue on the aberration study, they looked at different at the hyperparameters. So they evaluate the hyperparameter alpha with epsilon equal, epsilon equals 0.03. And they found from 0 to 2, and they found that it peaks at when alpha is 1, and that it starts to stabilize when alpha is greater than 0.2. And they also look at different epsilon value to compare the performance, and they found that it outperformed the baseline model.
Pardon me. Will, can you stop sharing your screen?
Okay, yes. Or I could give control to Quark if you want to. Or I could stop sharing.
What do you guys see the
Yes, we see it.
epochs? Okay. So another thing they looked at is evaluating the number of epochs during adversarial training. They found that regardless of the number of epochs, the adversarial examples outperform the baseline model. And if you look right here, with epsilon equals 0.07, it requires more epochs to converge for pre-training as compared to epsilon equals 0.03. And they found that as they increase the number of epochs, the convergence speed and embedding performance improved. So they also did a comparison of transfer learning. They trained both their algorithm and Sinclair on ImageNet 100, and they found that their algorithm achieves and Sinclair achieved 62.4 and 61.7 classification accuracy respectively, and they compared it to 8 other downstream data sets. If you look right here, their algorithm outperformed Sinclair in all but one data set, with the exception of pets, which had similar performance as Sinclair. And if you look at cars and airplanes, they had different. They had the lowest performance because ImageNet 100 did not have the class cars and aircraft. But even still, it shows that having adversarial examples does help improve the classification, even if the baseline model did not have the class with it. So they did a comparison with different attack methods. They looked at the following attack method at epsilon equals 0.03. They found that all the attack methods that they looked at outperformed the baseline model, and PGD performs the worst out of all the attack methods, while FGSM performs the best, while FGSM and RFGSM had similar performance as FGSM. So in conclusion, while previous constructive learning methods did not address the creation of negative, challenging negative example, this paper proposed a new algorithm that generates challenging negative examples using adversarial examples. And they found that the accuracy increased 1 to 5% compared to the baseline model. So for the strength of this paper, they managed to develop a new algorithm that produced hard negatives, proved that adversarial example can improve can be used to improve performance of other constructive learning frameworks, and provide extensive arbitration study that looks at their different hyperparameters and architecture depths. What is against for this paper is that they lack performance comparison for other data augmentation, such as cropping, cropping, rotation for super. Another against is they only looked at the resonant architecture. And while for the broader impact, they mentioned that this is great for time constraint and non-powerful hardware, they did not specify the hardware they use or the training time, how long it took to train. Any questions?